So what you see in the monitor there is what comes out of the processing of the central camera, one camera, and you will see different colors for different objects. So this is the image segmentation that we call image segmentation. So we take every single pixel in the image and we label that pixel. Again, it's a 4K 8 megapixel camera. And you have different classes, like for example, the pedestrians are red and vehicles are blue. And then pink is the free space, red curb, and white is lane markings, and then yellow is it is the traffic signs and traffic signals and so on. So these are all classes that we have already integrated into the system. Okay, so we're moving. We're moving now. You see the pedestrians are red, and you get a precise shape of the object. Okay, so this is the processing which is taking place. You can see the dark blue for the trucks and blue for cars. This is the processing is taking place on CV3 by just using one camera, the frontal camera, and you can switch on the multi-view. So the very same processing is running on all cameras. So the front, the left, right, back, and so on. So all the cameras are running the same detections, and you can see in the middle here we have the fusion of all low-level information. So remember, we're just talking about low-level here, so unfiltered. So this is the raw data that you get, and by analyzing these raw data, taking the data and again, this is only vision here. You will also have radar in a minute, and you will fuse everything together. So the other information that you see here is stereo information. So all these, let me see if I can change the point of view. Okay. So this is the, this is the tree in front of us here. This is the shape of the road down there. Can you see that? This is the island there. This is the traffic light, this one. So, and this is the 3D representation of what you have in front of you. Then, if you want, you can switch to a different view, and this is the tracking of the objects. So this is coming from vision and radar. So we fuse the two things, and detect objects and track each single object.
Okay. Now you're detecting objects. Are you actually identifying objects as well?
Yes, we have different classes, so we understand whether it's a motorcycle, a bicycle, or a car, or vehicle anyway, pedestrian. Maybe you will see the pedestrian here. See. Yeah, can you see it here?
What about a dog or a cat?
Oh, we don't have that, but I'll show you how.
It's okay, nobody does actually.
No, I'll show you one thing.
Yeah.
Because if you don't have that class, we still have the way of detecting that thing.
Yeah.
And I will show you in a minute how we do that.
What's the sampling rate for your guys' detection and identification?
What do you mean?
Is there a sampling rate at which it needs to be maybe faster than even the human eye can see, so that the cars can use that information to make decisions fast enough?
Or are you like 30 hertz right now? Or
maybe you got too close to the average. We're going 30 frames per second.
30 frames per second. Okay.
Yeah, exactly. So let me see if I can.
And that's sufficient for highway cruising, or the 30 frames per second?
Oh, 30 frames per second. We think it's enough for high speed driving.
Okay.
Yeah.
Okay.
Yeah. So I just wanted to show you a little bit more information about how we do the fusion. So this the car has been detected as a car. You can see that we get a shape, and this is monocular processing. So with just monocular, we get the classification of the objects, and then you add stereo vision, and with stereo vision, I will zoom in. Okay, so that's the result of stereo vision. That means that you can see all the little red bars. These represent, these are sticks coming from the stereo, and that represents the volume, actually the occupancy of the object.
Okay.
And then if you put together this information coming from vision and the radar information, you can put together the bounding box around that.
Right. And that's what that.
And the bounding box is the object.
Yeah.
So you just forget about all the flashing parts, which is the low-level information that you need to filter, and just focus on the bounding box. And this is what we have been doing during the ride.
Yeah.
So for each single object, we had a bounding box, and we were actually tracking that object. If you really want to see what, I mean, your question was about if there's something that you cannot recognize because it's not in one of the classes that we have, still stereo can detect that there's an object there. So you can detect the shape of the object. And you can see, for example, look at the back of the car. There's a wall there, and you can see there are those pixels from red to green. I can even change the point of view. And so just to give you an idea, these are the parking lot lane markings. This is the wall, and that's the post down there. So you can even get the shape of objects that you haven't been able to classify.
So it's not putting a bounding box because it doesn't classify it, but it does recognize it.
But recognize that there is something there. Exactly. And that's why we're using stereo here.
Yeah.
Because you get the 3D information anyway. So even if you haven't been able to classify that, so a strange object or an animal or whatever, you can still get the shape of that.
Okay.
Yeah.
Thank you.
Okay, so actually I meant that, I already mentioned that what we are doing now is that we are porting the remaining part of the autonomous driving stack that we already have on the other car. We're putting that in this car.
And next year we'll have the Ferrari.
Exactly. So I will show you the trunk.
Okay.
I'll show you the trunk and to show you how it looks like. And that's it.
Oh wow.
Wow.
Yeah, that's I think the most impressive thing.
So what's the total power consumption of that unit?
That box has 2 CV3s because we designed for future announcements, but we are only using 1 CV3. The peak power consumption of 1 CV3 is 50 watts. We are using less than that, far less than that, and there is still space for more processing on that chip. So now it's processing 18 cameras, 9 radar, doing the processing, doing the fusion, stereo, 5 stereos, and so on. And there's still space for more processing, and this is what we will add. And you can even touch it.
I was going to.
Yeah, touch it and see it's.
Yeah, you don't feel
it's
any
not.
heat or-
Yeah,
You feel a little bit of
Airflow?
but that's it.
so, exactly, but it's not not warm.
So
It's
there's
a
no
little
so
warm.
there's no fan. The airflow.
There's no fan.
It's passive.
No
There's
fan.
no
You
passive,
just
yeah.
feel a little bit of a temperature change. That's all you
okay.
feel.
So with what we've done here in the demo, it was all about detection and
Yes,
identification.
yes.
And so when you're talking about the processing power, it's with that. Now, with this, and I'm not too familiar with the CV3s, would they also be helping actuate, when we start getting to L4, are they going to be helping actuate, or would they pass on the data to like another ECU or whatnot?
The idea, the final architecture will be just one chip.
Okay.
Handling the
What about-
processing.
But for ASIL D, when you need 2 chips for redundancy,
That chip is ASIL B.
Yeah.
It has an ASIL D island.
yeah,
And the reason, because we put 2 chips in this board, is
Yeah.
that we want to be redundant.
yes,
Yeah. But
say-
this is for the future.
Yeah.
So, yeah.
You say the final thing would be 1 chip, but you can use multiple chips for higher level performance.
well,
Yes.
for high level reliability.
Yes,
Redundancy.
but maybe you can have 1 CV3, which
Yeah.
is the monster chip
Yeah.
and have some smaller one
Yeah.
that just can help you in case that fails.
Yeah.
And maybe you can run with reduced performance,
Yeah.
or go to a safe state.
Yeah, a limp along mode sort of thing where you need like a fault checking architecture.
Yeah.
So if something checks, you can basically go for a backup plan, backup some just basic functionality
Exactly.
for safety.
If you really want the same functionality, you have the same chip. But if it's too expensive, you can even have a second chip which is lower performance, and just use it to have some reduced.
Does the self-check occur in the CV3, or do you need an external chip?
That will be external, but then this is again for the future, for future architecture.
And this might be a few generations down after even we get through to level 4 and so forth. But with the single chip like that, do you foresee a situation where these things become mature enough where you might start having accelerators to do certain things that have been better understood, like especially on the actuation side, like if you're going to go, instead of doing it all on one big chip, kind of start distributing
But
it?
there's an advantage in doing everything concentrated.
Okay.
Because you get all the information from all sensors, and even the feedback from the car itself. So the speed and
Direction.
Direction, wheel speed, and so on. So if you are able to get everything together, that's a
Well,
benefit.
and if you have enough die area, you can always do it through a hardwired functionality on the chip.
Yeah, like chiplets and...
So what's the
Not even
connection
that.
between the sensors
IP
and
block.
It's MIPI.
MIPI? Okay.
Yeah.
Is there any intelligent pre-processing done at the so it's just raw sensitive?
It's just wires.
Yeah.
It goes directly to the chip.
Okay.
In the previous version, yes, we had the CV2 on its
Yeah,
camera.
right, yeah.
We're doing processing on the edge.
Yeah.
But now there's just wires.
And no compression on the video. It's all just raw stereo cameras.
So
And then,
raw MIPI going to the CV3?
Yes.
Wow.
And then you need 4K. Do you need 4K, or can you use a lower resolution around? And I see this is 2K.
This is 2K because you're just getting objects from 0 to 5 meters,
Yeah.
so you don't really need high resolution.
Yeah.
With that, we can do parkings very, very precisely already, up to the centimeter level.
Okay.
So we can do the Italian very tight parking lots.
Yeah.
And this is far enough. That's it. But for the front camera, I mean, if you have 4K, you can see much wider, much
Yeah.
far farther away. So that's the reason for pushing for 4K. And actually, it's a 4K stereo.
Yeah.
So you do the match of the two images,
Yeah.
the rectification, the match, and we do also online calculation. So when you take the two images, you align them, and then you can put the snap.
So, a question for you. Does it determine when there's a false positive on individual sensors, or after it creates the whole image?
No, actually, I'm sorry. I
A
didn't-
false positive, or false...
False positive. I mean, we are doing the fusion because of that. So we're not dealing with just one technology and the other
So
technology.
it does the fusion first, and then decides if it's correct.
So exactly to avoid that problem.
Yes.
Because you have two separate technologies, maybe the results are different.
Exactly.
How can you decide?
Yeah.
Yeah. But now we do the fusion at the low level.
Yeah. Well, and that's why you don't want to do the processing of the sensors.
Exactly. That's exactly it.
Yeah.
Yeah. And if you are able to do that in a concentrated way, there's a big benefit.
Now, they're holding a demonstration this afternoon where they're going to be running autonomous cars at like 160,
150 miles an hour,
150 miles
Yeah,
an
at the
hour.
racetrack.
So, can we see that demo?
Is the
Give me a Ferrari. Give me a Ferrari and do that.
Is the CV3 in that one?
Well, thank you very much.
Well, thank you.
Really
Thank you so much.
appreciate the
Thank
demo.
you.
Thank you for the demo.
Thank you.
Thank you very
Thanks.
much.
Yeah, thank you.
Thank you.